When you watch a car commercial, have you ever noticed that sometimes the wheels seem to turn backwards? Or sometimes you see a video of a helicopter and it seems like the blades are barely turning. But you never see that in real life, so what's going on there? And what does this have to do with yellow street lamps, or whether all four legs of a horse come off the ground when it runs, or the very surprising thing that happens if you stare and stare at your ceiling fan while it turns? Welcome to Inner Cosmos with me, David Eagleman. I'm a neuroscientist and author at Stanford, and in these episodes, we sail deeply into our 3-pound universe to understand why and how our lives look the way they do. And in this case, why the world looks the way it does. Today's episode is about visual perception and a series of really strange surprises about whether our visual systems analyze the world continuously, or instead, whether we see in frames like a movie camera. So, have you ever noticed what happens when you film a car going by on your cell phone camera and then you watch the video? When you look at the hubcaps on the car, say with some spokes on it or some pattern, when you look at the hubcaps, it looks like they're spinning the wrong way, or maybe they occasionally look like they're not spinning at all, even though the car is moving. So the first question is, why do we so rarely notice this? Like, why doesn't it blow our minds and we say, oh my God, that's not consistent with what I just saw with my own eyes and what I filmed? Why is it that we're so nonchalant about that? I'll be addressing that in some future episodes. But today, the main question I want to ask is, why does it happen? Why does the wheel look on your video like it's not spinning correctly, even though that's not what you just witnessed in real life? So to understand that, let's step back to the 1870s here in Palo Alto, California, where I am. So Leland Stanford, who was a wealthy industrialist and the governor of California and started Stanford University, Leland Stanford had some horses that he loved, and so he hired a guy named Edward Muybridge to take pictures of his horses running. Now, Muybridge was this really talented guy with a collection of cameras that could achieve shutter speeds of about 1/1000th of a second. And this was a really big deal in 1878. So Stanford and Muybridge wanted to take these really fast photographs of the running horses because no one had ever done that. And it turns out there was a debate about how horses arranged their legs when they galloped. And the question was whether all four legs ever come off the ground at the same time. And Stanford realized he could put these things together, his horses and this new photographic technology, to finally answer this question: do all the legs come off the ground? Now, if you've ever watched a galloping horse, you know that everything is moving just slightly too fast for you to confidently be able to answer this question. And so they needed a new way to address this. As an interesting side note, there were earlier paintings that showed a horse with all four of its legs off the ground when it was in the middle of a gallop. And in these paintings, the two front legs were extended in the air and the two back legs were kicked out behind the horse. But nobody really knew if this was possible. And right in 1878, this was the birth of chronophotography, which meant taking these fast pictures of complicated movements to really get what was happening there. So Muybridge set up a series of cameras on Leland Stanford's track in Palo Alto, and he took these photographs as the horse went by. And these photographs became very famous because of their clarity and because they answered the question. It turns out that all four of a horse's legs do come off the ground, but this happens when the legs are gathered underneath the horse rather than extended front and back. But what happened next is the important part. Muybridge took his very clear photographs and he put them in what's called a zoetrope, which is like an upright cylinder, like a big jar, with vertical slits in it. And you put the photographs inside the cylinder and then you spin the cylinder, and as it rotates, you see one of the photos through one of the slits. And then when the next slit rotates around, you see the second photo in that same spot. And then as the cylinder continues to spin, you then see the third photo through the third slit, and so on. And Muybridge was able to make the first prototype of a motion picture this way. And there's a very rich history to all the pieces that came together for movie technology over the next decades. But this is the main idea. Your brain sees picture one, and then picture two, and then picture three, and it interprets that as smooth motion. Now, this is exactly how modern movies work. On a video you watch on your cell phone, you look at a snapshot of Tom Cruise with his left foot in the air, and then another still shot of him with his foot a little lower, and another with his foot now touching the ground. And in the next photograph, his right foot is a few inches off the floor. And as long as you flash these snapshots quickly, then it looks like he's racing down the sidewalk after the bad guy, and you're totally caught up in the emotion of the scene, and not even considering that your visual cortex is being fooled into believing something, motion, that is not actually there. Now, what strikes me as interesting is that we are so used to this that it's difficult to recreate for ourselves the absolute shock that people must have had when they saw this phenomenon for the first time. I mean, how stunning would that be to witness a series of still shots looking like they were moving? Keep in mind that in the entire history of the world before this moment, no one had ever had a chance to capture photons from the scene, make a photograph, and then swap those out so rapidly that it looks like smooth motion. It wasn't, in fact, even until 1868 that somebody made a flip book. You remember those little books where you hold your thumb to zip through all the pages rapidly, and it looks like smooth motion of some drawing? And although the zoetrope was around with little hand drawings since 1866, no one had done this with photographs until Muybridge did. Before that, no one had ever seen motion pictures. I mean, just imagine the next time you're watching a TikTok video that a smart person like Benjamin Franklin went his whole life without ever seeing a moving picture. And just imagine how gobsmacked he would be to see that. And remember that this technology was so stunning that it came to be called a move-y, as in something that seems to move, and we still call it that. Okay, now, how does this work exactly? So whether you're talking about a zoetrope or a flip book or a movie projector or what happens on your cell phone screen when you're watching a YouTube video, it's all the same thing. It relies on the phenomenon of apparent motion. So what is apparent motion? It's a visual illusion that occurs when a series of still images are shown in rapid succession, and you get this perception of continuous smooth movement. So that is the basis for the zoetropes and the flip books and modern films and videos. Now, the reason this works is because the brain retains the impression of the previous image for just a brief moment after it's disappeared, and that creates a smooth transition to the next image. And this phenomenon of apparent motion is closely related to a different phenomenon called the persistence of vision, which is that your brain holds onto an image for a split second after it disappears. And that allows you to perceive smooth motion even when there are gaps between the individual images. Like when you're spinning the cylinder, the zoetrope, you see a flash of image one, and then you don't see anything while the cylinder spins a bit more, and then you see a flash of image two, and then you don't see anything, and so on. But your brain clocks the image and retains it long enough that it bridges the gap between. So it's because of apparent motion and persistence of vision that we can make and enjoy motion pictures or TV or video games or virtual reality. Okay, now there's one more concept that's important here. Imagine that I held up the first photograph of Muybridge's horse, and then I picked up the second picture and I held that in front of it. And then I took the third picture and held that up and so on. I'd be going way too slow to fool you into thinking there's motion. You might cognitively get it that there's a sequence being shown, but you wouldn't have the direct perceptual experience of motion. But if I flash the photos quickly, then it works. So how quickly do I have to flash these? So to get at this answer, you can do a simple experiment where you just flash an LED light on and off and on and off. And if you're doing it slowly, like flash, flash, then you see a flashing light. If you do it more quickly, like flash, 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 then you still see that it's flashing, but of course it's a bit faster now. But now do it just a little bit faster than that, and suddenly the flashing light looks solid to you. You can't distinguish this from a light that's just on. So the speed of flashing at which the light suddenly looks like a continuous light is called the flicker fusion threshold, because suddenly the flicker fuses to look like a solid. Your brain just can't see the fact that the light is turning on and off. So, movies only work when the successive images are flashed faster than the flicker fusion threshold, so that you don't see one photo and then the next and the next, but instead you see a smooth transition. Now, how fast do you need to flash it? Well, the exact threshold that you can measure in people, that changes a bit when you're talking about the size of the thing flashing and the intensity and whether it's black or white or color. But generally, you need to flash something like 40 times per second, and then it looks smooth. Now, as a quick side note, you may know that old movies were shot at 24 frames per second. So why didn't people see a flickering between the frames? The answer is that movie projectors would flash each frame 2 or sometimes 3 times before going to the next frame. So you had a flicker of 48 or sometimes 72 flashes per second. So the whole thing looked smooth. And similarly, television is traditionally shot at 30 frames per second. And in the same way, all the frames are doubled. Phones, by the way, typically use 60 refreshes per second, although a lot of high-end phones have an even higher refresh rate. So the point is, when you look at any of these technologies, movies or television or phone, they're all flickering above the flicker fusion threshold. And so everything looks wonderfully smooth. So when you're walking around in the world, a lot of lighting can look like it's continuous, but you can demonstrate to yourself that it must be flickering because of strange effects that you can get. For example, many cars have moved to LED headlights or blinkers that flicker. And you can't tell that when you're looking right at the light. But if you move your eyes to the side, you'll see a series of images of the headlight or the blinker because it hits your eye in different spots when it comes on. Or take those yellow street lights that you see. They're called sodium vapor lamps. And even though it looks like a solid light, they're actually flickering on and off with the alternating current, which is 60 times a second in America and 50 times a second in Europe. Now, the light looks solid because it's flickering faster than the critical flicker fusion frequency. But if you swing your hand around, you'll notice a strobing effect. You'll see multiple locations of your hand that are spaced apart. And the amount they're spaced has to do with how fast you're moving your hand. So when you see these sorts of effects, that's how you know something is actually flickering, even though it looks solid to you. Okay, so we see how movies work by flashing a bunch of images, and even though it looks like continuous motion, it's actually discrete frames. And this trick has revolutionized the way that we communicate information compared to 200 years ago. We have YouTube and TikTok and television and video conferencing and so on. Cool. But this particular trick of stringing together discrete frames can yield strange illusions. And people started noticing these things during the first days of movies. So originally, the movies were Westerns with wagons, and the wagon would be rolling forward along the dirt road, but it often looked in the movie like the spokes were turning the other way. Or sometimes the spokes would look like they were turning the right way, but not at the right speed, or sometimes not turning at all. So why does that happen? Well, imagine the wagon wheel turning clockwise. The camera captures a frame where the wheel is in this position, and then when the next frame is captured, some tens of milliseconds later, the wheel has turned a bit and the spokes are in a slightly different position. But here's the tricky part. All the spokes look alike, and so your brain's job is to figure out how the spokes in the first frame match up to the spokes in the second frame. And generally, it can only do this by looking for the shortest distance that things must have changed. So let's say the spoke has rotated 90% of the way to the position of the next spoke. The brain will erroneously think it has rotated the other way. Because from frame 1 to frame 2, your brain sees that the shortest distance is not a rotation this way, but a rotation the other way. And so, this effect came to be known as the wagon wheel illusion. And now that you're going to keep an eye out for it, you're going to see this everywhere. In car commercials, the wheel doesn't appear to be turning correctly, but instead, the turning of the hubcap seems to run the wrong way sometimes, or slow down in its rotation to a halt, even though the car is zooming down the highway. And you can see this with helicopters or drones on your television or on your phone. It always looks like something is wrong. The rotor blades are hardly turning at all, or maybe they turn the other way and the helicopter lifts up, even though it doesn't make any sense. There's no adequate spinning to make that happen. This is all the wagon wheel effect. Okay, so now we are all set up for an observation that came as a big surprise in the neuroscience world. Some colleagues of mine published a paper in 1996 pointing out that you could get these kind of motion illusions not just in movies, but in real life under a continuous light. Now, this was a big claim because it suggested the possibility that our brains are actually seeing in snapshots like the frames of a video camera. Is that true or not true? Well, I'm going to come to that in a second. But first, I want to tell you how to experience the illusion. So, if you have a ceiling fan that's turning, lie back on your bed and stare at the fan. Do this in the middle of the day with no lights on, so there's no flickering lights, there's only sunlight. Now, let's say your fan is turning clockwise and you stare at it, you'll see that it's turning clockwise. But if you stare and stare long enough, occasionally you will see it turn the other way. For just a second or two, the fan seems to reverse direction. So please try this, although it might take a few minutes of just staring and staring at it before you see it. But you'll know when you see it, the fan suddenly runs backward for just a moment. Now, I just want to be clear that you can see this illusion in the day under sunlight. So this is not explained by something like a subtle flickering of the lights because of the electrical current. Now, this illusion with the fan seems like a subtle thing that no one would care about, but it caused a lot of discussion in the neuroscience community when this was noticed. Even one of my mentors, Francis Crick, the co-discoverer of the structure of DNA, he wrote about this too. And I'll tell you why it was such a big deal to neuroscientists, because it wasn't clear why this would happen in the visual system, which seems to be taking in information continuously. So the hypothesis that took hold was that maybe the brain is taking in the world in frames like a movie camera. And this is what the researchers who found this suggested. They suggested that vision might be like the filming of a spoked wheel with a video camera, and that perhaps this illusion with the fan was evidence of discrete perception. In other words, that we see in frames like a video camera. Now, if the claim were true, that's a big deal. But I started to suspect that something wasn't right here. Because first of all, there are some important differences between watching the fan in the daylight and watching the wagon wheel effect in movies. First, in the movie, if you have the wagon rolling at a particular speed, the wheel seems to be going backwards at a fixed speed the whole time. But that doesn't happen with the fan. It only happens for just a moment after you've been staring at it for a while. Second, when you see the fan reverse, it seems to happen at a faster than normal speed, even though in the movies, the reverse spinning of the wheel is always slower. And third, in the movies, sometimes the wagon wheel effect can look like the wheel is stopped because the camera keeps catching the wheel when the spokes are in the same position, so it looks like nothing's turning. But that never happens with the fan in daylight. You never see it look like it's stopped. And little problems like that started making me suspicious that maybe the wagon wheel effect in movies and this issue about the fan reversing under daylight had only a superficial similarity, and the two effects had totally different reasons for actually happening. And I really wanted to understand this very fundamental point about the visual system. So what I did is I drove to the pawn shop and I bought an old record player for $8. And then I spent $2 at the art store to get a circle of styrofoam. Picture this like a big hockey puck. And then with my student Keith Klein and my colleague Alex Holcomb, we put evenly spaced black dots all around the outside of the styrofoam puck. And we put that on the record player. So when you flick on the record player and look at it from the side, you see these little black dots moving from left to right. Now, why did I use a record player instead of a computer screen? Because the computer screen inherently has a frame rate, and I wanted to make sure we were really doing smooth motion here, continuous motion. And the way this experiment goes, when you watch this record player in the daylight next to a big window with no lights on, that's how we made sure there was no flicker that influenced anything. When you stare at these smoothly moving dots going from left to right, and you keep your eyes in one place and you stare and stare for a few minutes, it eventually works. You see the stream of dots suddenly reverse direction. Just for a few seconds, it looks like they're zipping from right to left, and then you see things going back to normal again. So we were able to reproduce the illusion, but now here was the important trick. We now placed a mirror right next to the record player. So now what you see are two pucks rotating side by side in opposite directions. So you're seeing one stream of dots moving left to right, and the other reflected stream of dots moving right to left. Now the question is, do you see both streams of dots reverse direction at the same time? Or do you see one puck reverse and then maybe later the other puck reverses and then the first puck reverses again? If your visual system is snapping frames, and here we have to assume that the length of the frames are changing for some reason. If your visual system is snapping frames, then both pucks should reverse at the same time, because that's what would happen if you were filming with a video camera whose frame rate was changing. But if the two pucks reverse independently, that suggests something very different is going on. So you keep your gaze fixed right in the middle between these two streams of dots, and what happens? What happens is you see one puck reverse, and then the other, and then the first one again. And this result seems to rule out snapshots, because again, if our brains processed visual information like a camera in discrete frames, then you would expect both sets of dots to always switch directions at the same time. But that's not what happens. Now, you might argue a point here, which is that because I had people stare right in between the dots, they were seeing one puck in the left hemisphere and the reflected puck in the right hemisphere. And what if perhaps the two hemispheres of the brain both do snapshots, but with independent frame rates? So I addressed that frame in 15 seconds by turning the whole contraption on its side so that you could see both pucks in the same hemisphere. And you get the same result. The pucks reverse direction independently at different times from one another. So it appears that the visual system is not taking snapshots. But what is the explanation here? Well, you have some populations of neurons in your visual cortex that detect rightward motion. And when those are active, you say, there's clearly rightward motion in the world. But you also have populations of cells that pick up on leftward motion. And these populations are always balanced in a competition. But here's the key. For technical reasons that you can read about in my papers on this, it turns out that those leftward populations can sometimes be fooled by a lot of rightward motion. They get a little bit activated by the wrong direction of motion. And so even though your brain is 98% sure that the motion is to the right and the rightward population is screaming with activity, there's a little bit of activity in the leftward population as well. And as I said, these left and rightward populations are always in a rivalrous relationship with one another. And so every once in a while, the leftward story wins for just a little bit. In other words, because of this battle going on under the hood between different explanations, the leftward motion detectors are intermittently able to drive perception for just a moment. Now, if you listened to my episode about the dress and other illusions, this is very similar to other things that we've seen, like with a cube that's drawn as just the wireframe of the cube. You can see it coming out of the page one way, or you can see it coming out the other way, and those perceptions will switch back and forth. Now, which orientation the cube is in, that happens to have a 50-50 chance that it might be one way or the other. But here, what happens with the ceiling fan reversing, that's more like your brain saying, okay, 98% chance it's moving this way, and only 2% chance it's moving the other way. So almost all of the time you see it correctly. And only once in a great while will the underdog neural population win, and then you'll see it the other way. You'll see this illusory reversed motion for just a moment. Now, because this is much more rare for the underdog to win, you have to stare at the fan for a while to see the illusion. So what we've seen here and in other episodes is that you have populations of cells in your brain that are fighting for different interpretations of the world. And it's always just a matter of which population dominates the hill at any given moment. That's what you perceive. And it's all because your brain is locked in silence and darkness, and it has to put together a story of what's going on in the outside world based just on little trickles of data that it can pick up on. That's why there's so many different types of illusions. So let's wrap up. This kind of thing happens a lot in science where two different phenomena sort of look alike, like the wagon wheel effect in movies and the illusory motion reversal of the fan. And so we don't know if there's one explanation underlying two things, or they're actually underpinned by very different things. As Carl Sagan said, science is always alternating between lumping and splitting, meaning that sometimes you realize that two disparate phenomena are actually the same thing, and then you can lump them together. And what happens equally often is that two things you assumed were the same are actually different phenomena. So illusory reversal of the fan under sunlight appears to happen not because the visual cortex is snapping snapshots, but instead, even weirder, because of different political parties in your brain engaging in their parliamentary debates. So this simple set of experiments gave us real insight into what was going on and led to 4 publications. And, a lot of neuroscience is very pricey to run. And so I was very pleased that the total amount I spent on these experiments to address a very fundamental point about the visual system was $10. One of the joys of life is careful observation of what is actually in front of us, figuring out how we're actually seeing the world. Because we make lots of assumptions about what we're seeing, but if you observe carefully, you'll start to notice all the very weird things that your visual system serves up to you. And after this careful observation, you can sometimes set up simple experiments to understand what's actually happening under the hood. And as we practice that, we get deeper insight about how our brains are actively constructing the reality that we typically take for granted. Now, if you want more detail on any of these experiments, please find my papers at eagleman.com/podcast. You'll always find references there for further reading. Send me an email at podcast@eagleman.com with questions or discussion, and I'll be making an episode soon in which I address those. And check out and subscribe to Inner Cosmos on YouTube for videos of each episode and to leave comments. Until next time, I'm David Eagleman, and this is Inner Cosmos.